So I'm going to walk through the solution of a practice problem. If you haven't tried it, just pause this video and give it a shot. This one is our last one, hypernatremia. So this is when a patient has really low sodium levels. They're going to act really confused. They can actually end up in a coma. So to treat hypernatremia, a patient is going to be given a 3% sodium chloride saline solution by IV. Now, normal saline solution is 0.9% sodium chloride. This is isotonic with normal cellular fluid. So let's go through and take a look at each of these questions. So the first one is asking, is this 3% solution hypertonic, hypotonic, or isotonic? Well, for it to be isotonic, it would need to be the zero point 0.9. So that's iso. So that means since it's at a higher concentration, it'll be hypertonic. Now, the next question asks, how is this going to relieve the patient's symptoms? Well, there's kind of two ways. First, by adding in such a concentrated solution of sodium chloride, we're going to be adding in sodium ions. So that'll be able to replenish some of the ions in the body. But we also have the effect of adding in a hypertonic solution means that we'll have water inside our cells be at a lower concentration than the fluid outside of the cells and the cellular fluid. So we expect to see that water travel across the cell membrane and actually reduce the volume of our cells. And that'll actually increase the concentration of the sodium particles already in the cells before any of it's even replenished. All right, for C, we're asked what is the concentration of the sodium chloride solution in units of molality and molarity? We're going to assume a density of the solution of 1.1 grams per milliliter. So we know that our 3% solution is mass per volume. And so that's going to be the mass of sodium chloride divided by the volume of the solution times 100. So at this point, I'm going to do something crazy. I'm just going to assume a volume because this concentration value will be the same no matter how much of it I actually have. So I'm going to assume 100 milliliters. Remember, when we do mass over volume, our volume units are always going to be in milliliters. Whereas for molarity, we would always use liters. So I'm going to assume 100 milliliters, which means that my mass of sodium chloride is going to be 3 grams because my 3% will equal, I'm solving for the mass of my sodium chloride. So solving this, my 100s cancel out. 3 grams is what my mass of sodium chloride will be. Give myself a little bit more room here. Okay, so with this, I can actually start working towards molarity and molality. I need to know the moles of my solute. So I'm going to take that 3 grams and convert it into moles. Doing a simple mass to moles conversion using the molar mass that I'll calculate from the periodic table. And for sodium chloride, it's 58.44 grams per mole. And that's going to give me 0.0513 moles. So this is really my moles of NaCl. All right, cool. Now we have a little bit more information. We have to start thinking now about the denominator of each of our concentration equations. For molarity, I'll need units of liters. For molality, I'll need kilograms of solvent. So let's start with the molarity. It's a little bit more straightforward. If I have 100 milliliters, I need to just convert this. So this is for my total solution. So this will be my that I assumed to get that 3 grams. So the 100 milliliters converts into zero point 0.1 liters, just using a dimensional analysis, quick metric conversion. Now I would need to know the mass of my solvent, right? To be able to calculate molality. And right now I'm just getting all of the pieces of this together, and then I'll be able to calculate my conversions. So if I'm curious about the mass of my solvent, I'll find this by subtracting the mass of my solute from the solution because I've got the mass of my solute. That mass of solute is that 3 grams that we just calculated. So let's find this mass of solution. I know I have zero point 0.1 liters or 100 milliliters, and I've been given a really helpful piece of information that the density of the solution is 1.1 grams per milliliter. So I'm going to start with that 100 milliliters that I assumed in the beginning, and I am going to multiply that by my density that was given in the problem. They'll give me 110 grams of my solution. Um, and so I will then take that and subtract that, my solute from that. So my 110 grams minus my 3 grams gives me a mass of my solvent that is 107. Now, if I wanted to convert this then into kilograms, oops, I'm going to perform another metric conversion going from grams to kilograms. And so for each kilogram, I have 1,000 grams, or 0.107 kilograms. All right, now I have all the pieces to my puzzle that I need. I have my mass of sodium chloride. Actually, I don't need that, sorry. Now I have all the puzzle pieces that I need to calculate molarity and molality. I have the number of moles of my solute. Great. I have the volume of my solution in units of liters. And I have the mass of my solvent in units of kilograms. So my molarity is going to equal the moles of my sodium chloride divided by the volume of my solution. That's going to be equal to that 0.5 or 0.513 moles divided by my 0.1 liters. That's going to give me 0.513 molarity. For my molality, again, I'm using the moles of my sodium chloride, but now I'll use the mass of my solvent on the denominator. So that'll be that 0.0513 again at the top. But now I'm going to divide this by 0.107 kilograms. So similar, but slightly different. And for this, I get 0.479 molal. And that is my concentration. So it's a little bit of a longer problem, but these are all dimensional analysis conversions. The more difficult part is seeing that overall strategy to get to our concentrations when we're doing these types of conversions from one to another. So they take some practice. All right, let's look at our next question. What does the freezing point and boiling point of the 3% saline solution look like? So let's calculate the freezing point and the boiling point. So for both of these, freezing point and boiling point, we're going to start from the pure solvent and find the correction factor to get to the freezing point or the boiling point of the actual solution. So we know that the freezing point for water is always equal to 0 degrees Celsius. Great. We are going to assume that the Van Hoff factor is 2. That's the theoretical Van Hoff factor. That 1.9 is for a 0.05 molal solution. And so since we don't know the exact, that doesn't match our molality, we'll go with our theoretical value. So our Kf, this is a value that you would look up or that would be provided to you, is 1.86 degrees Celsius per molal. And the molality that we just calculated was 0.479. So much larger than 0.05. So I would expect that our Van Hoff factor is less than 1.9 and definitely less than 2, but we'll stick with our theoretical. All right, so with this information, I can just plug into my equation. So that change in temperature for my freezing point is going to be equal to my, let's write out the equation first. Van Hoff factor times the molality times the Kf, which I believe actually is negative, sorry. And I missed that on there. So we've got our 2 for our Van Hoff factor, our molality of 0.479, And then we'll multiply this by our negative 1.86 degrees Celsius per molal. And that'll give us the change. So this will be how this is different from 0 degrees Celsius. And when I plug this in, I get a value that's negative 1.78 degrees Celsius. So my freezing point for my solution is going to equal 0 plus the change in temperature. So it's going to be minus 1.78 degrees Celsius. So that's negative 1.78 degrees Celsius. It's a lot of writing the same thing over and over. So that's how we get our freezing point. So our freezing point is going to be lower than 0. It'll be not too much lower though, negative 1.7. Now let's look at our boiling point elevation. So our typical temperature for boiling is for water, our solvent, is going to be 100 degrees Celsius. Now our Van Hoff factor, we're going to stick with our theoretical Van Hoff factor for our sodium chloride of 2. We've got Kb for water that's equal to positive 5.512 degrees Celsius per molal. And then our molarity molality is going to be that 0.479 still. So the change in temperature for my boiling point is going to be equal to that same equation. We're just replacing the Kf with a Kb. So our Van Hoff factor times our molality times Kb. So we're going to have our 2 times our 0.479 molal times our 0.512 degrees Celsius per molal. Plugging that all into my calculator, I get a value that is equal to 0.49 degrees Celsius. So the boiling point temperature for my solution is going to be equal to 100 degrees Celsius plus 0.49 degrees Celsius. So 100.49. Not very much of a difference. So coming back to our problem, I know this is a long one, going through each of our colligative properties. Now we're going to look at vapor pressure. So in E, if the vapor pressure of the water at room temperature is 23.8 millimeters of mercury, what is going to be the vapor pressure of this saline solution? Now it's worth noting that our sodium chloride is a non-volatile solute. So we won't have to worry about the vapor pressure of the solute when we do this. All right, so the equation that we're going to use for this to calculate the vapor pressure of our solution, we're going to call this P of solution. That's going to be equal to the mole fraction of our solvent times the vapor pressure of just the pure solvent on its own without anything added to it. So we know that that vapor pressure for the pure solvent is that 23.8 millimeters of mercury. So our goal now is to calculate that mole fraction of the solvent first, and then we'll be able to get the pressure of our vapor pressure for the solution. To get the actual moles of solvent instead of solution, we have our 0.107 kilograms that we can start with, right? So this is the mass of our solvent. I'm going to convert this into grams, just with a quick metric conversion. And then I'm going to use a mole to mass to mole conversion using just the molar mass of water, which is about 18 grams per mole. So I'll multiply this by 1 mole divided by our 18 grams. And when I do that, I get a value that is, I get 5.94 moles of my water. So that's just the mass of my solvent converted into moles. All right, so now I can actually figure out my mole fraction. So my solvent goes on top, that 5.94 moles, and then it's going to be divided by the total number of moles in the solution. So that's the 5.94 moles plus the moles of our solute, which was, if we pull from our previous work that we did at the, I think, part C, that is going to be our 0.0513 moles. Very small number compared to the solvent. So plugging this into my calculator, I get a value that is 0.991. So my vapor pressure for my solution is just going to be that 0.991 times the 23.8 millimeters of mercury. So they'll be very similar. And what I get when I plug this into my calculator is 23.6 millimeters of mercury. And so that's going to be the vapor pressure of my actual solution. All right, last one. So for F, we're asked to calculate the osmotic pressure. So osmotic pressure has the equation with the fun to write capital pi symbol, that it's going to be equal to the Van Hoff factor times molarity times our R value, which is that universal gas constant, times temperature in Kelvin. So we already calculated our molarity. Great. We're using our theoretical Van Hoff factor, which is 2. The molarity we calculated again was 0.513. Our R value, we need to use something that has atmospheres in it. So that way we calculate it in atmospheres. Although if you use a different one, like if you use for millimeters of mercury, you could calculate it in millimeters of mercury. I just prefer atmospheres. I don't know why. So you could do 0.0821 or 0.08206, either one. Liters times atmospheres divided by moles Kelvin. And then our temperature is always going to be in Kelvin for these. So that way we don't have a zero number. It's 298 at room temperature. So plugging these into my osmotic pressure equation. So after I plug that all in, I'm like plugging this into my calculator. So pretty straightforward. I'm going to get a value that's 25.1 atmospheres. So that would be my osmotic pressure for this solution, this hypertonic solution.